Today, I will be doing an application of Stokes Theorem. So what Stokes Theorem says is that first I need to set up a couple things. C is a closed curve, or closed simple curve, meaning it doesn't intersect itself. S is a surface with boundary. C, okay, the curve C. So let's draw a picture of this. We're gonna, that's good enough. Okay, so we're gonna have some surface, right, with some curve C. And what I'm gonna do is I'm gonna have a surface that has a boundary of C. So right here is my surface. And right there is C. Okay, it's going to be going in that direction specifically for this. Okay, so I'm going to have R parameterizes C, and S parameterizes S. So what I did here was make it so that these are of T and S of S and T. Okay, those are going to be my two functions. So what it says is that if I look at the line integral, and it's going to be counterclockwise specifically, line integral counterclockwise, of some vector field f along C times the differential in respect to our parameterization. It's going to be the same thing as the surface integral of the curl of our vector field f times the differential in respect to our t, our s. So might not be completely visible, but yeah, you can see it better. So let's turn it on there. Okay. So what's the intuition behind this? I don't really have any. This is the theorem. So let's do an application of this. So we're gonna have where I'm just gonna parameterize them first. Okay. So I'm gonna have the curve parameterized by this. So it's gonna be 0 I hat, and it's gonna be 2 plus 2 cosine t j hat, and then it's gonna be 2 plus 2 sine t, 2 plus 2 sine t j hat. Okay, so this is going to be our curve and our vector field f going to be given by, and I'll write it, so it's x to the third e to the 5z I hat plus, and it's going to be x cosine y j hat, and then the other one is just going to be a simple 3y dz. Okay, and I want to figure out the line integral on this closed curve C. Okay, f dr. Okay, so let's just do it normally. So what do I get out of this? Well, I get integral, and t here is between 0 and 2pi. That's very important because now we can just put those in here. And then we're going to have f, which is going to be x cubed e to the 5z I hat plus sine yj hat plus 3y k hat dot product, and I'm going to do the differential in respect to r. So what's that going to be? Well, what you need to realize first is that I need to plug in for x, z, and y the parameterizations. Okay? Okay, so what's x? Well, it's 0. So these two terms, these first two terms, just go away because x is 0. Multiplying by 0. Okay, what's this? In terms, well, what's y? It's going to be 2 plus 2 cosine t, right? So it's going to be 3 times 2 plus 2 cosine t. Yeah, I just plugged in for y, and now this is going to be k hat, and that's the only one left. I do the dot product with dxi hat plus dyj hat plus dz k hat. And we're doing it in respect to t. And, oh, sorry. And because I've already plugged in t, I just need to multiply it by z, right? Or z prime. I need to multiply it by z prime, the derivative of z. So right in here, no, that's the wrong thing. Z right here is 2 plus 2 sine t, so the derivative of that is going to be 2 cosine t, right? dt. Sorry, this right here is dz sine dt. So then, multiply it by dt, I get dz, which is what we wanted. Okay. So now what do I get? Well, I get integral. Well, first let's factor out 3. Right there, let's factor out a 2, so 6. There's a 2 right there, so 12. 12, integral 0, 2 pi. And then we're going to have 1 plus cosine t times sine t dt equals 12 integral 0 to pi. And we're going to have cosine t plus cosine squared t dt. But now, can you see that? No, you can't. It's just there. Let me turn this off. Okay, so now you can probably see it better. Okay, so now, what do I get out of this? Well, it's going to be 12. What's the derivative, antiderivative of cosine t? It's negative sine t. No, it's just sine t. Sorry. And plus, if you do the antiderivative of cosine squared t, you get 1/2 t plus 1/4 sine t from 0 until 2 pi. Now this is going to be 12. Okay, plug in 2 pi, sine 2 pi plus 1/2 2 pi, let's see, plus 1/4 sine 2 pi. Subtract off of that everything evaluated at 0, which, unsurprisingly, everything in there just goes to 0. And we're left with sine of 2 pi, 0. 1/2 2 pi, it's going to be pi. Plus 1/4 sine of 2 pi, 0. So in the end, we get 12 pi. So that's how you evaluate the line integral directly. Now, using Stokes Theorem, what we can do is say that this is actually going to be equal to the integral over S, the surface integral, curl F ds. Okay, so what's S going to be? S of S and T. Well, I'm going to put it in terms of R and T, and you'll see why. It's because if I were to graph this actual function on the actual curve on the XYZ plane, what you get is a circle centered at 2, 2 with a radius of 2, right? 2. So then I can parameterize it as 0 I hat plus, and then 2 plus 2r cosine t, j hat plus 2 plus 2 sine t k hat. What I'm doing here is I'm letting r just slowly approach it. So given any r, I can just go along that radius line. Okay, so now ds is going to be given by s for surface integrals, s r cross s t, the determinant of I hat, j hat, k hat, and then 0 in respect to r, that's going to be cosine t. In respect to r, that's going to be sine t. There's 2's in column, sorry. Okay, right here, I'm going to have negative 2r sine t for partial derivative in respect to t, and 2r cosine t. Okay, so what am I going to get out of this? Well, I hat's coefficient is going to be 4r cosine squared t minus negative 4r sine squared t on j hat. What's it going to be? Well, 0, because those 2 zeros are right there. K hat also going to be 0. So you can just ignore them. What you can do here, factor out 4r. Here we have cosine squared t cosine squared t. And it's just going to be 4ri hat. Now, after you've done that, what we have to do is find the curl of f. So remember that we have it that ds equals 4ri hat d s d or dt dr. Sorry. Okay, so then next we find the curl of f, which is going to be given here in evaluation. Okay, now we're going to have down here x component x cubed e to the 5z, and here x cosine y, right here 3y, even though it doesn't look like it. Okay, I part. d on dy times that's going to be 3. Okay, d on dz there. There's no z there, so it's going to be 0. Okay, j hat, what's it going to be? Well, it's going to be derivative in respect to x of that, nothing. Derivative in respect to y of that, nothing. 0 there. And then plus k hat. And what's it going to be? Well, I messed something up. I should have done the derivative in respect to z there, not y. So I'm going to get j hat 5x cubed e to the 5z. Okay, and I'm going to have k hat's coefficient as cosine y 0. So cosine y. Okay, so now I have the two things I need. So now I'm going to do integral. So we had that t is going from 0 to 2 pi, r is going from 0 to 1. Now I'm going to have this 3 right here dotted with that. So I'm going to get 12r dt dr. Okay, it's going to be 12 times the integral from 0 to 1. I'm going to have rt from 0 until 2 pi dt or dr. And it's going to be equal to 24 4 pi integral 0, 1 r dr equal to 24 pi 1/2 r squared from 0 to 1. I get 1/2, get it 12 pi. And that is the same, and that's an example of Stokes Theorem in action.